There's this powerful, totally invisible force that's shaping everything around us, from massive bridges all the way down to the tiny little parts inside your watch. Today, we're going to pull back the curtain on that force and explore the fascinating world of thermal expansion. I mean, you've definitely seen this, right? Those big, droopy curves and power lines on a super hot day, or those deliberate cracks built right into concrete sidewalks. Ever just stopped and thought, hey, what's the deal with that? Well, it turns out the answer to both of those questions is exactly what we're diving into today. So, the whole secret starts at a level you can't even see, the atomic level. When you heat something up, you're basically giving its atoms a massive jolt of energy. They start vibrating like crazy, just buzzing back and forth, and they start pushing against their neighbors, demanding a little more personal space. Now, that tiny little push, multiplied by trillions and trillions of atoms, well, that's what causes an object to physically get bigger. Okay, so this atomic level dance party makes things bigger, but how they get bigger is where it gets really interesting. Physicists have broken it down into three really clear categories, and it all depends on an object's shape and dimensions. First up, we've got linear expansion, which, as the name suggests, is all about length. Then you have superficial expansion, which deals with a two-dimensional area. And finally, there's cubical expansion, which covers the whole shebang, the total volume. Let's take a quick look at each one. Let's start with the simplest one, linear expansion. Just picture a long, thin metal rod. When you heat it up, those atoms start vibrating and pushing outwards. Now sure, it gets a tiny bit wider, but the most obvious effect, by far, is that the rod just gets longer. That's linear expansion in a nutshell. Okay, now let's scale up to a flat surface, like a metal plate. When you heat this up, it doesn't just get longer, it gets wider too. The entire surface area actually grows, and that, my friends, is superficial expansion. And finally, we get to a 3D object, like this cube. Heat it, and it expands in all three dimensions at once: length, width, and height. The entire volume of the object increases. We call this cubical, or sometimes volumetric expansion. So you're probably wondering, how do we predict all this growth? Well, scientists use something called the coefficient of linear expansion. You can just think of it like a unique fingerprint for every material. It tells you exactly how much that material will expand for every single degree the temperature changes. It's the secret sauce for engineering things that can handle the heat. Right, solids seem pretty straightforward, but what about liquids? This is where things get a little bit tricky because, when you heat a liquid, you almost always have to heat up its container too, and that container is also expanding. This picture here shows you exactly what's going on. When you apply heat, the glass flask actually expands first, which, believe it or not, can make the water level drop for just a second. Then, as the liquid itself starts to heat up, it expands way more than the glass, and the level shoots up. This creates a really interesting puzzle. How in the world do you measure the true expansion of the liquid when its container is changing shape right underneath it? To solve this, scientists came up with two key ideas. First, there's apparent expansion. That's what you can actually see with your eyes and measure, the final rise in the liquid level. But then there's real expansion, which is the true absolute increase in the liquid's volume if you could somehow ignore the container's expansion altogether. And the solution turns out to be this beautiful, simple formula. The true, real expansion of a liquid is just the apparent expansion you see, plus whatever the expansion of the vessel was. It's a clever way that lets us figure out the liquid's true change in volume, no matter what its container is doing. Pretty neat, huh? All right, enough theory. Now that we've got the basics down, let's look at some tangible, real-world consequences. Because this isn't just about lab experiments. Thermal expansion affects our daily lives in ways you might not even realize. So let's imagine a little scenario here. Let's say you have a glass flask that holds exactly 400 cubic centimeters. You fill it completely to the brim with mercury on a pretty normal day. Now, what do you think is going to happen if you heat that whole thing up by a whopping 80 degrees Celsius? Well, it turns out that mercury expands way more aggressively than glass does. The math shows that even though the glass flask gets bigger, the mercury tries to get even bigger. And the result? You get a spill. Specifically, 5.58 cubic centimeters of mercury overflows. It's a perfect practical example of how different materials have different expansion rates. Okay, here's another puzzle for you. Think about something as simple and reliable as, say, a metal measuring tape. Do you think a little change in the weather could actually affect its accuracy? Oh, absolutely. It's wild. If you have an iron measuring rod that's perfectly accurate at a cool 10 degrees Celsius, but then you use it to measure a 2-kilometer distance on a hot 40-degree day, that rod will have physically expanded from the heat. The result? Your measurement is going to be off by almost a full meter, 0.96 meters to be exact. It's a tiny percentage for sure, but over long distances, that adds up to a massive error. We've seen how heat can mess with volume and length, but for this last example, wow, we're going to look at something truly mind-bending, the surprising way that temperature can literally change our measurement of time itself. Just think about an old pendulum clock. It's all a fascinating chain reaction. On a warm day, the metal rod of the pendulum expands, it gets longer, and basic physics tells us that a longer pendulum swings more slowly. Well, a slower swing means the clock's gears advance more slowly, which causes the clock to actually lose time. And the numbers here are just staggering. For a typical brass pendulum clock, an increase of just 5 degrees Celsius, that's just the difference between a cool morning and a warm afternoon, will cause it to lose almost 5 seconds, 4.92 seconds every single day. Heat is literally slowing down time. So we'll end on this thought. We've just seen how a few degrees of temperature can make power lines sag, throw off our measurements, and even change the speed of a clock. It really makes you wonder, doesn't it? What other powerful, invisible forces are all around us, constantly shaping the world we think we know so well.
Thank you for watching my video. Please like, subscribe, and hit the bell icon.